Hi everyone, this project is about characterizing the rheological properties for polydisperse and monodisperse colloidal rod system. We have two material, HCl, which is a polydisperse system aspect ratio range from 50 to 2500, and PA, which is a monodisperse system aspect ratio which is 1306. It's a potential rheological modifier using fabric and home care product. It helps to crystallize surfactant inside typod and release it during the degradation. According to Solomon Spicer, the colloidal rod system can reach gel phase when there is low volume fraction with strong attractive interaction. The strong attractive interaction in this study is depletion interaction driven by depletant. Take PA as example. With increased depletant concentration, the system trends from the single PA rod phases to the transitional region when bundles start to form, and then to the gel phases when the bundle connected with each other to form the sample spanning network. And the system is measured by systematically change the concentration of depletant and polyethylene oxide PEO, and the stabilizing surfactant, linear alkyl benzene sulfonate LAS, and the colloid HCO or PA. According to our measured data, we separate the experiment into two regimes: the LAS2 colloid equal to 16 and the LAS2 colloid greater than 16. We use multiple particle tracking microbiology and PT to measure the rheological properties for both PA and HCO. We use microscope to record probe particles Brownian motion, then use multiple particle tracking algorithm to get the probe trajectory. From the trajectory, we can calculate the mean square displacement (MSD) and the logarithmic slope of MSD alpha. When alpha is 1, the material is in liquid state. When alpha approaching to 0, the material is in gel state. And when alpha in between these two values, the material is viscoelastic solid gel. By comparing the alpha with critical relaxation exponent n, which is analyzed from the time cure superposition, when alpha greater than n, the material is in solid state. When alpha less than n, the material is in gel state. And when n greater than 0.5, we have loosely associated network at the transitional point, which dissipate energy, and when when n less than 0.5, we have tightly associated network at the transitional point, which stores energy. So we're going to present our data for PA first. First from the MPT, we find that the diffusivity of the probes in the PA rapidly decreased when PO concentration and is increased from 0.3 to 0.35 at the LAS2 PA, which have this MSD gap here, which indicate that the transitional point might between these two concentration, and then we find that the alpha decreased consistently with increasing PEO concentration, which indicate that PA system structure become arrested, and this is independent of colloid and LAS concentration. And then we use TCS to analyze our MSD data. We first get the critical depletant concentration for PA, where we find that it is constant with increased LAS to PA ratio. And also the critical relaxation exponent n is lower in LAS to PA equal to 16 than in LAS greater than 16, which indicate that at LAS 2P greater than 16, we have loosely associated network at the transitional point, and when LAS 2P equal to 16, we have tightly associated network at the transitional point. And we think this might related to the zeta potential of the system. So we measure zeta potential, and we find that zeta potential is inversely related with alpha and n value when we change the LAS to PA. And so at the LAS to PA equal to 16, the system is in a single PA rod phase where constrained probe motion. And when LAS to PA greater than 16, the system is in a aggregation phase where the probe freely diffuse. And now we present our data for HCl, and we find that similar to PA, the critical depleting concentration for HCl is constant with increased LAS to HCl. And also zeta potential and N value are inversely related when LAS to HCl change. And by comparing the N value for HCl and N, we find that they are similar. So in conclusion, HCl and PA have the same critical values when LAS to colloid is changed at the phase transition. And the different LAS concentration lead to different starting structure of the colloidal system, regardless of the identity of the colloid. And the CC is constant with increasing LAS to colloid.